Lecture 1.19 is about, um, very simply, a little review of what I did today. And I'm trying to also go over question 1 and 2 for those people who thought that I moved a little too quickly. Okay? So today's lecture is just really quickly about Avogadro's hypothesis. Now, as I explained in class, Avogadro, okay, Count Avogadro, made a very important hypothesis and contribution to the dilemma of chemistry at the time. At the time we had reactions, let's just say we had like a reaction up here. Um, let's say we're going to make this reaction of say, hydrogen. Okay, we'll say hydrogen and fluorine. All right, fluorine to make hydrofluoric acid. Okay, we know it's hydrogen plus fluorine, and we're going to make maybe HF. Okay, now let's take a container. Let's put hydrogen in there. Let's take fluorine and put a fluorine in there. And we should make and watch our volumes combine to make hydrofluoric acid. The problem is we don't get one box to one box to one box. In fact, in nature, okay, when we did this, and I don't know if Gay-Lussac actually did this one, but we would actually get two volumes here. And the reasoning is because these guys are diatomic. That means you would actually have to have another one here, and notice you'd have to make two of them. Okay, so very clearly this would have a 2 in its balanced reaction coefficient. And there's the balanced chemical reaction. As we talked about, we can make good cookies and cake because now we know how much of each of them, but more importantly, we know what the chemical formulas are of the individual particles. So we can predict the boxes and go back and forth. Just like if I was to give you, let's say, nitrogen, hydrogen to make ammonia. Okay, and notice one particle for each same size box. That's Avogadro's hypothesis. Same volume, same temperature and pressure, same number of particles. Now a particle, it's very important you understand this, a particle can be, and that's very important, can be an atom by itself, or it can be an atom bonded to something else like itself. These are all different types of possibilities for particles. Amedeo Avogadro considered these all to be molecules. And he said, when you have these seats in a theater, at least that's the analogy we're using, we only have a certain number of seats. In my drawings here, I have one seat. And notice that it can be bonded to itself or other different particles. So one seat gives you a certain type of volume. Okay, so if this is 10 liters, this has to be 10 liters, same number of particles. I don't care if the particle changes. I don't care if the particle is just an atom. Okay, I don't care what the size of the particle is. How many particles you have determines the space. So same number of particles, same volume. That's Avogadro's hypothesis. Same volume, okay, at the same conditions of temperature and pressure, you have the same number of molecules. That was Avogadro's, Amadeo's hypothesis, which means we can now use Gay-Lussac's values. So back to this, nitrogen, hydrogen. We did this in class, and it's also part of your homework. Now, how do we figure out what's inside? We're going to do what was done, a little opposite of what I'm asking for class, but we know when this reacted, it took one of these, 3 of these. These boxes are supposed to be the same size, so I'm sorry if my drawing is failing you. And we get 2 of these. And this is all they knew. They didn't know anything about the chemical formula. We made ammonia, which is a stinky, okay, pungent smelling gas, and this is hydrogen and nitrogen. They don't know the formulas. Didn't even have the symbols. So if you want to go by Dalton symbols, I don't forget what the symbols were. Maybe like an egg that we're drawing. Any case, let's move on. What's inside these boxes? Okay, well, if you think nitrogen was by itself, let's draw 1. Let's say hydrogen is by itself. Let's draw 3. You may think, well, if they come together, they're going to be like this. Notice this is 1 seat. This is 1 seat. These are all the seats in the theater. And this is 1 seat. Terribly drawn. Okay, let's get rid of those things because they're around there. And, oh, that's not going to work out. All right, let's go scroll down. Okay, so let's get rid of that entire box because I'm not liking how it looks. So what am I getting at here is that, let's redraw that one. So 1 nitrogen and 3 H's. There we go. Nice. Okay, looks like a bad hairdo. Now, what do we got here? This is not working out for me. I'm missing a total volume. So just as we talked about in class, they figured out, well, the only way to explain that, I would have to make 2 volumes. I need another particle. Double the volume. If this is 10 liters, this is 10 liters. These all little guys here are 10 liters. I need another particle. I'm getting 20 liters collectively of ammonia. Notice the only way for this to work is ammonia must be NH3. Okay, so this doesn't work. If there was just 1 box here, not 2, then this would be the right type of particles. So what they think of is that maybe this is bonded to itself. And it was confirmed through other reactions in this one that this in fact is the case, that these guys are diatomic, and my friends in chemistry, that these would combine. So these would combine, okay, to form another particle. So again, here are 10 liters. And if you notice, my screen just changed a lot because my computer froze, probably because of the million things. I got 10 liters here, 10 liters here, so we got a total of 20 liters. Okay, so obviously we had twice the volume because we had to create a whole new seat or another particle. Now this particle, of course, is bigger than these, but again, the size of the particle does not depend on the volume. The volume depends on how many positions you can fit. And particles, again, can be big, like in terms of ammonia, and they can be smaller in terms of, let's say, hydrogen. Or they can be even smaller, like helium, just 1 atom. Okay, so hope that helps out a little bit. Let's go to your homework real quick, and we'll pause here and get to your homework page. Okay, magically, your homework appears. We have the first 2 to do. And we're going to convert, so we take 24.45 grams of copper chloride. And we want to convert to moles. We want to convert to a how many number. And there's a grams here. And I know that 1 mole equals how many grams? Well, if I've got a box of copper chloride, what does that really mean? Well, that must mean that I have on every seat in my theater, I've got a copper and 2 chlorines bonded together. Now, what does that mean? Well, if I have every 1 particle or every 1 mole, if I have a mole, that means I have 22.4 liters of these compounds in a gaseous state. And that's my particle, my copper with the 2 chlorines. That's my particle. Now, that particle is in 1 position. Now, we know in a box, in that seat there, there's more than just 1 of them. But who cares what the actual number is? We determine that how many fit in this box under current temperature and pressure, or we'd say STP, standard temperature and pressure, okay, that in this 22.4 liter container, we're going to say we have a mole, and a mole represents a certain number. We're going to learn about that number tomorrow. And I could care less, but that real number is 6.02 times 10 to the 23. It's a huge number of particles, okay, that fit in 22.4 liters. Now, what does it all mean? Well, these number of particles represent that many, but it's too cumbersome to use, so we're going to say a mole. A mole represents that many particles that fit in that box. So, all of these particles have to equal some number of grams. Well, if I've got 1 mole or 1 box of copper chloride, I have a mole of copper. And if I just had copper in the seat, and that many of them, that many seats, it would equal 64 grams. Now, where am I getting that? My friends, in chemistry, I'm getting that from the periodic table. Check it out. Notice the word relative atomic masses. These are relative atomic, they're based on each other. So let's go find good old-fashioned copper. Okay, for those Latin lovers out there, it's cuprum, okay? And in any case, 63.5, that's the mass number. We don't care about the proton number. We don't know about this yet. This is the mass number, and it means a box of copper is approximately 64 times massive than the lightest element, which is hydrogen. So there you go. Okay, so a box of copper, all right, is 64 grams. So I have 64 there. But I have 2 chlorines. In one box, I actually have twice as many, or 2 moles of Cl. Now, what's the mass of each Cl, or chlorine? Let's go to the periodic table. Let's go find chlorine. And there it is, Cl. And we're going to see that its atomic mass is 35.4. What does that mean? That means a box of just chlorine atoms, 22.4 liters, or I'm sorry, 22.4 liters at STP, standard temperature and pressure, equals 35.4 grams. So I'm going to round it to 35 right now for simplicity's sake. And we're going to come up with 35. But if I have a mole of copper, a box of copper, I have 64 grams. Well, I have 2 moles of chlorine atoms, right? For every one of these particles, there's 2 chlorines. So if I've got a mole of copper, I have 2 moles of chlorine. So I have to times this by 2. And that gives me 70. And then I'm going to add the 70 plus the 64 together. So that's something called a formula mass. We'll talk more about that later in the year, but this is what we need to do now. 70 plus 64, and I have 134 grams for every mole. That's my converting factor, and that goes right here. Okay, and now I can find the answer. Put it in my little later of calc. 24.5 times 134, and divide by, I can do this, 24.5 divide by 134, and I get 0.183 moles. And what does that mean? Well, it's 1.83 or 18.3% of this big number, but it's a reflective value of how many particles I have. Okay, if you're an egg farmer, you would use dozens. We're using moles. Okay, let's go and do this one. I have 2.31 moles of C2H6. All right, party people, I want to get rid of moles, so mole goes in the bottom. What's the grams? I need my converting factor. Well, if I've got a box of C2H6, that means I've got a container on each seat. I have 2 carbons. So in a mole of these, don't I have 2 moles of carbon? And if I go to the periodic table, let's go find our carbon. And lo and behold, right there is 12. A box of just carbon atoms, 22.4 liters, okay, is 12 grams. Let's get out of here. So this becomes 12. That's 12 times 2 because you have 2 moles. 2 boxes would be 24. What else do we have? 6 H's. Per each seat, we've got 6 H's. So if we've got a mole of seats, or this many of seats, it's going to be 6 moles of hydrogen. Well, if I got a box of hydrogen, how much does it mass out to be? 1 mole of hydrogen. I keep saying a box, but same idea. All right, I go find my good old-fashioned H. All right, probably too big, and there it is, 1 gram. Okay, there's the relative atomic mass. Relative because it's based on each other. And it's 1, and I get 6. Add them together because it's a total mass, and we have 30 grams per mole. And that 30 goes here, and that's my converting factor. Moles cancel, and very simple, 2.31 times 30. And that gives me 69.3 grams. Notice I'm maintaining 3 sig figs. You start a conversion with 3, you end with 3. These numbers you're getting as standards. Okay, it's a little quick how we do the homework. Okay, see you tomorrow.